I'd like to now talk about the arrangement of d orbitals in the coordination compounds. Now the d orbitals are on the central metal, and I just want to remind you what we're talking about when we're talking about d orbitals. You'll remember that we have done stuff about electron configuration back in General Chemistry 1. And we have 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. And here's the 3d, this is what we're most interested in. It's 5 orbitals. And on an uncoordinated metal atom, that is a metal that doesn't have anything attached to it, it's just going to be 5 flat d orbitals, all the same energy. As soon as we attach stuff to it though, these begin to take on different arrangements, and we're going to be talking about those right now. Alright, so if it's an octahedral arrangement, that's very similar to what we've been dealing with up to this point with the cobalt, the first example we looked at. And it turns out that we get 3 d orbitals down here and then 2 d orbitals up here. If it's a tetrahedral complex, that is with 4 things attached to it. Let me show you what I'm talking about. That's a tetrahedral there. Here's an octahedral here. In those instances, the tetrahedral, we get 3 d orbitals up here and 2 down here, so it's almost like these two are reversed. Alright, so let's see what reasons there might be for that. So these are the 5 d orbitals, and remember that orbitals are just places where you can expect to find electrons. And for example, in the dxy orbital, you expect to find the electrons between the x and y axes in this kind of shape. So they're not along the axes, they're lying in between the axes, and that's kind of important. The xz, they're between the x and z, and the yz, they're between the y and the z orbitals, y and z axes. Now these two, on the other hand, your x squared minus y squared and your z squared, the x squared minus y squared lies on the actual x and y axes, while the dz squared lies on the z axis, like that. Now these black things that are coming in, these are, since we're making an octahedral type arrangement, these are the 6 ligands that are actually attacking the metal, and they're attacking along the x, y, and z axes. Now because these orbitals actually contain electrons, and then these ligands are going to be negatively charged, what's going to happen is these are going to actually interact with the negative charges, and these are going to be of higher energy. Now these here that lie in between the axes aren't directly interacting with the negative charges of the ligands, so those are going to be of lower energy. So what this results is what's called DD splitting, where you've got these 2 up here and these 3 down here, the ones that directly interact being higher energy and the ones that don't interact being lower energy. And that's what we get for an octahedral arrangement. Now a tetrahedral has 4 things coming in, and these 4 things are coming in between the axes, not down the x, y, and z axes directly, and you can see that's what I've tried to present here. So what's going on is that the ones in between the axes, these particular orbitals here, will interact with the ligands a lot more than the ones that lie directly along the axes. So the dxy, dxz, and dyz will be of higher energy because they're interacting with the ligands, and these will be of lower energy because they're not interacting with the ligands. So it's important to differentiate between the octahedral and tetrahedral arrangements because they're going to have different arrangements for their d orbitals. Now remember, this only happens when we attach things to a central metal. The other thing that's going to be important, and this would be for an octahedral arrangement here, is that the energy in between these 2 layers of d orbitals can be varied, and the variation is completely dependent on the ligands attached to the central metal. So we've got this table here which gives us an idea of strong field ligands and weak field ligands. And the dividing line is pretty much here where the water is. I consider these to be strong field, I consider these to be pretty much weak field. Now strong field ligands, what happens is that if you have 6 CNs, like this one here, attached to the iron, that's going to lead to a very, very large difference in energy between the top level of d orbitals and the bottom level of d orbitals. Remember, this is your dx squared minus y squared and your dz squared. Alright, it's these two here, and the other three are going to be down the bottom. And that difference leads to a different way of putting the electrons in these orbitals. Let me show you how that goes. Alright, so let's say we've got our strong field ligand. It leads to a very large difference in between these two orbitals. And we've got 5 electrons. I'll show you how to figure out how many electrons we're going to put in. We're going to put 5 electrons in here. According to Hund's rule, I have to put 1 in here, then 1 in here, and 1 in here. Now these are too far away for me to put electrons in there as well. So what I'm going to do is I'm going to put 1 in here, and then 1 in here. But I have to put 3 here separately first, because they're the same energy, and then I put the other 2 in. Now let's contrast that with the other one. This is called a when we've got a weak field ligand. We've got 6 waters here attached to be Fe3+ now. So we've still got 5 electrons to put in, but because this energy is so small, these are treated like they're almost the same energy as these, which means that when applying Hund's rule, I put 1 electron here, 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 and here, and they all go into these separately. So 1, 1, 1, 1. That's because the energy difference here is so low. This energy difference is going to be completely dependent upon what ligands we have attached to a central atom. If it's a weak field ligand, this distance will be small, and we'll put the electrons in accordingly. If it's a strong field ligand, like these here, this distance will be large, and we will put the electrons in accordingly there as well. We call this a high spin complex because we've got lots of unpaired electrons, and we call this a low spin complex because we don't have very many unpaired electrons.